Hi, in this video series, I'm going to show you how we at Solara Technical go about defining a complete power system. I'll post these videos every week on Thursday, so please watch for them. As discussed in our last video, I'll be designing the power system for our passive optical network using a parallel copper network, like the one shown here. It consists of a Class 1 48-volt power supply. Class 1 circuits are considered unlimited energy and must be installed accordingly. The power limiters are 100-watt Class 2 outputs, which can be run by cable technicians outside of conduit. These 100-watt circuits, along with the fiber, feed each optical network terminal. These ONTs, in turn, convert the fiber and power into power over Ethernet ports used to power any variety of loads like cameras, computers, and telephones. In this slide, you will see both the power network and the optical network. Note how the output of the optical splitters are combined with the DC power limited copper pair into a hybrid cable designed for this purpose. In my design example, I'll assume we can power each ONT with a single 100-watt power feed. When a load requires more than 100 watts, it's possible to run parallel 100-watt Class 2 feeds to a power combiner. The output of this power combiner is no longer a Class 2 circuit. It's a Class 1 output and needs to be handled accordingly. Here's a typical representation of a building and how the network might be powered. In this case, Class 1 circuits are distributed to each floor where they are converted into Class 2 circuits to power each ONT on that specific floor. To complete this portion of our power system design, the customer needs to tell us the total number of ONTs and their power draw. Remember, we design from the outputs back to the inputs. They need to also tell us which model ONT they plan to use. I'll assume a Tel Labs 140W model optical network unit. This is what that unit looks like. The important specs for us are listed here. Note the maximum PoE output of 72 watts, the input voltage range of 48 to 56 volt DC, and the idle power of 5 watts. I'll transfer these numbers to my spreadsheet. The customer told us the maximum PoE power used will be 43 watts, below the maximum available of 72 watts, so we know the ONT can supply the load. To allow for connector losses, I'll use 49 volts as the minimum for the ONT, even though the spec allows 48 volts. The maximum input current is computed by adding up the load power and the idle power and dividing both by the minimum input voltage. Our customer told us the maximum distance from the power limiter to the ONT is 350 feet. Since we need to account for a round-trip voltage loss, I'll double that number to 700 feet. The maximum voltage loss I can allow in the Class 2 distribution is the maximum output voltage of the power limiter, or 56 volts, minus the minimum input voltage allowed at the ONT, in my case, 49 volts. So the maximum loss allowed is 7 volts. It's helpful to think of each Class 2 pair as a long extension cord that we are sizing. Given the maximum voltage drop of 7 volts and the maximum low voltage input current of 0.98 amps, the extension cord must have a total resistance of less than 7.15 ohms. Using the maximum length of 700 feet, I calculate 10.2 milliohms per foot, or a wire gauge of number 20. Now that I have the total ONT power load and the total cable loss, I can compute the output power of each power limiter to be 54.7 watts. The power limiters are actually DC to DC switching converters with active electronics. As such, there's an efficiency to this conversion of 93.4%. The input power for each converter is the output power divided by this efficiency, or 58.6 watts in this case. Our customer told us there are 260 ONTs to be powered for a total of 15,236 watts. For this application, I'll be using this power limited system. It has 4 power modules, each with 8 100-watt power limited outputs for a total of 32 outputs per shelf. Back on my spreadsheet, I figured out that I need 9 shelves of power limiters to supply the 260 ONTs asked for. Each shelf has a minimum input voltage of 42 volts. Each shelf will need 45 amps at 42 volts to power 32 ONTs and their extension cords. Assuming number 2 wires to supply the 45 amps over 10 feet, the total class 1 48 volt power needed is 15,262 watts. The battery I plan to design with has a float voltage of 54.5 volts. The class 1 48 volt output needs to supply 280 amps at 54.5 volts just to power the passive optical network. Thanks for listening. And if you need help with anything related to power, please reach out to us. It costs you nothing to chat. Until next time, have a great week.